So there are two main problems that calculus stems from. So the first main problem that calculus stems from is the tangent line problem. Right, and we know that the tangent line is stemming from the derivatives, right? So you're really asking, how do quantities change at an instant? How does something change, right, that instantaneous rate of change, the derivative? The second main problem that we try to conquer in calculus, one of the big questions behind calculus, kind of like why this sort of math was invented or created or discovered, however you kind of want to look at that situation, right, is how to find the area under a curve. Which is really asking the question, right, how does a quantity accumulate over some sort of time or interval, anything like that? So you've found area under curves before, right? So you've taken a geometry class before, you know how to find your area of basic shapes. So, right, if we were talking about a geometric approach to area under a curve, right, we have like a little graph going on. And maybe we look at the equation f of x equals 2x, and we're going to look at it over the interval from 0 to 2. Right, so if we graph the function from 0 to 2, we have a y-intercept of 0, and so just a slope of 2, right, so up 2 over 1. Right, and it just creates a nice little triangle. So as we're trying to find this area, right, that's just a triangle. We know how to find that. The area is just equal to 1/2 times the base of 2 times the height of 4. So our overall area is going to be 4 units squared. Right, but in terms of more of like calculus question, and even then this example is going to be pretty straightforward. We're going to look at much more in-depth functions eventually. Right, so now instead of having same basic function, right, now let's look at a function like 2x squared, but over the same interval. Now we'll count by 2's on our y-axis. Right, except now it's curving, right? It's got a little bit of a curve to it. And so now to find that area, right, it's not quite a triangle. There's a little bit of concavity there, it's curving, right? So eventually in calculus, we are going to learn how to find the exact area under the curve. But before we look at that, we're going to look at different ways to approximate the area and kind of show where the actual exact answers are going to be coming from. So one way to approximate the area of a region bounded by a curve, and normally the x-axis, normally we're looking between a curve and the x-axis, is to use what's called a Riemann sum. So a Riemann sum is named for 19th century German mathematician Bernhard Riemann, and it's used to approximate area. So the area under a curve is approximated by partitioning the region into rectangles. Right, so you find the area of each rectangle and add them all together. Right, so pretty straightforward. We're just going to be splitting up the area that we're trying to find the total area of into geometric shapes that we know how to find the area of, and then we're going to add up all of those little areas together to get the overall area approximation. So something that's important to note for Riemann sums is that the rectangles that we're going to use can either have equal width or unequal width, meaning that they could all be different widths. So typically in AP calculus, if we give you the actual equation of the function and ask you to create the Riemann sum, it's probably going to be with equal widths or equal partition. But one thing to watch out for is in questions where they give you a table of information, because those will not always be equal width. So you really want to pay attention to the differences between your x coordinates and all of that good stuff. So we're going to do a couple of different problems. Well, we're going to look really at one area and how to use various different Riemann sums to approximate it. So we're going to look at basically one example problem, but we're going to do it 3 different ways. So for our example, we're going to use a Riemann sum. So that just says, so like when they say Riemann sum, they mean rectangles. If they want you to use a different geometric shape, they'll tell you that. So we're going to use a Riemann sum with 4 equal subintervals. To approximate the area under the curve f of x equaling 2x squared on the interval from 0 to 2 using ... And this is where the different methods are going to come into play. So we're going to do the same problem 3 different ways and kind of show how you can get different approximation values and kind of think about what's the best one to use. So the first way that we're going to do this is we're going to use the right endpoints. So this is a pretty straightforward graph, very easy to sketch. So I'm going to go ahead and sketch it for each problem that we do. Let's see, so I got... Okay. Okay, so if we sketch that, right, y-intercept at 0, if I plug in 1, I'm going to get 2. And if I plug in 8, if I plug in 2, I'm going to get a y-coordinate back of 8. Just trying to kind of really accentuate the fact that it's curved by giving it a good scale. Okay. So we want to try and approximate that area. And I know I'm going to have to draw this graph again later, so I'm just going to go ahead and copy that for later. Okay, so we want to use the right endpoints, and we want to partition it up in 4 equal subintervals. So that tells us that the rectangles are all going to have the same width, right? So we know that to find the area of a rectangle, we got to know the length times the width, or the height times the width, however you want to phrase it. So the width of each of our rectangles is going to, we also call this the delta x. So we're going to let the width of the rectangle fall along the x-axis. And all that's going to be equal to is we're going to take the length of our interval. So we have 2 minus 0. So our length is 2, and we're going to split that up 4 ways. So we're going to get 2 over 4, or 1/2. So I'm going to go ahead and draw those kind of splitting up points here. So we have 1/2, then we would split at 1, and this would be 3/2. So we want to use the right endpoints. So we're going to draw our rectangles in. So I'm going to go to the right endpoint of each kind of subinterval. So we have 4 subintervals going on, right? So we have 1 subinterval here, 1 here, right? So 4 little different widths there. So I want to go to the right side of each of those and then draw up to the curve and then make myself a little rectangle. So go to the right hand side, draw up to the curve, draw my rectangle. Right, so now I can see I'm going to find the area of each of these. Right, so overall right now I can tell that this is going to be an overestimate of what the actual area is, because our rectangles are circumscribed. So our rectangles go over the area that they go outside of the area that we're actually trying to find. So the height of each of these is actually the function value at the right side, right? So we want to know these heights. Right, so it's just going to be the function value evaluated at the endpoint. Right, so when we go to find our area, Right, we're going to say it's approximately equal to, and just we're going to find the area of each rectangle. So the first rectangle would be 1/2 times the function value at 1/2, and then we're going to add that to 1/2 times the function value at 1. Right, and then our third rectangle has a height at the function value of 3/2, and our final rectangle would have an area of 1/2 times the height at f of 2. So you can also think of this, of course, as you can pull out the 1/2, so that seems easier than writing it next to all of them. And then if we evaluate the function values there, right, f of 1/2, if I plug in 1/2, I'm actually going to get back 1/2. F of 1 is going to give me back a 2. If I plug in 3/2, I'm going to get back 9/2. And if I plug in 2, I'm going to get back an 8. Okay, so 9/2 plus 1/2 is 10/2, so that's 5 plus 10. Okay, so we're going to get 1/2 of 15, right? Right, which is going to be 7.5 or 15/2. You can think of it either way. So we have an over approximate at 7.5. So we know it's less than that. So another way that we can use a Riemann sum is you don't have to use the right endpoint. You can, of course, use the left endpoint. I didn't mention this before. You can abbreviate these. So some people, for right endpoints, they'll call this RRAM. And that stands for right endpoint, right Riemann approximation method. And so they would call the left endpoints LRAM. Not everyone does, so that's why you don't really have to worry about that. Okay, so I'm gonna just drop our graph back in here and erase the G that came with it. There we go. Okay, so if we go for the left endpoints now, so we're still gonna have those same subintervals. Right, so we still have those 4 different rectangles in here. Right, so we still have our rectangle width at being 1/2. That's not going to change for any of these problems because we're not changing how many intervals we're breaking it up into. So now we're going to actually use the right endpoints. The left endpoints. So you go to the left side of each of your partitions and draw a rectangle. So now this one's tricky. Well, not really. It just seems a little weird because we're actually going to draw a rectangle with 0 height, right? And then at our next interval, maybe we'll color code these. Right, we go to the left-hand side, draw up to the curve. So we're going to be finding this area. Right here, we go to the left-hand side, draw up. And then, oh, I already used that one, whoops. And then here, right, go to the left-hand side and draw up. So now we can see that here we're going to have an underestimate. Right, it's very clearly an underestimate because there is, area that we want to be finding that's outside of where the rectangles are. So in other words, these rectangles are inscribed, so it's going to be less than what it actually is. So again, our height is going to be the function values, so we don't have to worry about that. And I wish I could spell. So we're going to start by saying the area is approximately, right, we always want to be careful that we are using an approximation method, so we should be showing approximation symbols. You don't want to say exactly equals because it's not exactly equals. We just said it's an underestimate. So if we go ahead and find the area, I'm going to leave the width factored out here. So it's going to be 1/2 and then times all of those different heights. So the first height would be 0, so f of 0. And then we're going to do plus the second height is at f of 1/2. Right, the third height, that blue rectangle, is at f of 1. And then my fourth rectangle is starting over at f of 3/2. Right, so you can use your calculator or, of course, plug them in with your brain. It's not that hard of a function. So now that I have that it's approximately equal to that formula, I'm going to simplify the formula, which is why I can switch over to an equal sign itself. So again, I'm going to leave the 1/2 factored out. F of 0 is 0. F of 1/2 is 1/2. F of 1 is 2. and f of 3/2 is 9/2. Okay, so 9/2 plus 1/2 is 10/2, which is 5. 5 plus 2 is 7. So we get 1/2 times 7, which is 3.5. So we have an underestimate happening at 3.5. So right, overestimate was 7.5, underestimate is 3.5. So it's somewhere in between those two numbers. Okay. So the third type of Riemann sum that we can set up, right, we did the left side, we did the right side, we can go straight down the middle. So this is called a midpoint sum. And some people will abbreviate this as MRAM for midpoint Riemann area approximation method or whatever you want to say. Okay, so again, I'm going to cheat and drop that graph back in. So we're still going to have these partitions split up with the same width. Right, so we still have these three rectangles. So do a little bit of color coding. What color am I using? We'll use hot pink, whatever. Okay, so our width is still 1/2. But now our height is going to be a little different. So if we go ahead and draw our rectangles in. So what we're going to do is for each of those 4 subintervals, so I'm going to zoom in really far on the first one. So I'm going to go over and I'm going to find the midpoint. So that's going to be at 1/4. I'm going to go up to the curve, put my point there, and then draw my rectangle on. Right, and so for my next one, right, I'm going to go in the middle. So between 1/2 and 1 would be 3/4. I'm going to go up to the curve, find my function value there, and then draw my rectangle. Right, same thing going all the way across, going to the middle here. So in between 1 and 3/2 is the fraction 5/4. So going up to f of 5/4. So this is definitely a question where graph paper comes in really handy. And then my last one would be, so between 3/2 and 2, right, you're really just finding the average of those numbers, but that's going to be 7/4. Right, going up to the function at that value, and then drawing my rectangle in. So we can see that these are probably going to be a little closer, right, because some part of the rectangle is outside of the region, and then there's some parts that are not, right? So we have like some parts that are overhanging the region that we're actually trying to find, but then there are some parts inside the region that aren't covered by any of the rectangles. So this is probably going to be a little closer for an approximation, right? So our height here is going to be the function of the midpoints. So if we go to set up our area approximation, we're going to say the area is approximately that 1/2 times, I'm going to just leave it factored out here since we're going to multiply it by all of those heights separately. So that's going to be f of 1/4 plus f of 3/4 plus f of 5/4 plus f of 7/4. So now, if this is a calculator active question, I would just use a calculator for speed. If you're using a graphing calculator, I would put this equation into your y1 if it's not already there, and then use your table feature if you set it up for ask, so that way you can plug in whatever function values you want. That way you just have to type in your x values over and over again. So I've already done this problem, so I already have the answers written down for each part. So let's see, our function at 1/4, if I plug in 1/4, you get back 1/8. F of 3/4 is 9/8. F of 5/4 is 25/8. And F of 7/4 is 49/8. So super convenient since they all have the same denominator. So 1/2, and then let's see, that's 84/8. And if I multiply, and I'm just going to reduce while I do that, that's going to give me 21/4. So I can say this is 21/4, which is also just 5.25. right? So if we look back at our previous answers, we knew that the underestimate was at 3.5, so this is a little bit, above that, and it's a little bit below 7.5, which was our overestimate. It's not perfectly in between them. If it was perfectly in between them, it would be at 5.5, but pretty good overall estimate, right? Almost exactly in the middle. So there's one more section of this lesson that I want to teach you, but before we go on to that, I want to start with your OYO, because your OYO is going to kind of be in two parts. So I want you to do the same thing here. So you guys are going to set up 3 different Riemann approximations. So you're going to use a Riemann sum, and you guys are going to do 6 equal intervals. You're going to do 6 equal subintervals. To approximate the area under the curve of f of x equaling negative 1/2 x squared plus 2x. And you're going to look at that over the region from 0 to 3. Again, you're going to do this 3 different ways. You're going to approximate using the right endpoints, the left endpoints, and the midpoints. You can leave your answers as decimals or as fractions, whatever you prefer here. Okay, so the last part of this is just a way to write these summations. So the example that we just did had 4 subintervals, so that wasn't super hard to write out, not super hard to evaluate, but sometimes we're looking at functions that are a little bit more intense or that might have a lot more intervals. Because you can imagine if we increase the number of subintervals, so if we are splitting it into 10 subintervals or 20 subintervals, right, our rectangles get super narrow, but we're also going to be covering more of that area. So it's going to be getting a little bit closer and closer to our approximation. So we can use something called sigma notation to help us kind of shorthand these abbreviations, and our graphing calculators, or if you don't have a TI-84 at home or a TI Inspire, whatever calculator you're using, you can also use Desmos graphing calculator, and I'm going to use that on my iPad because that's accessible to everybody to actually evaluate these for you. So we're going to use sigma notation to evaluate this, and I'm going to show you what sigma notation is. So sigma notation is, of course, so sigma is a Greek letter. So sigma itself, so my sigmas are never great, but it's that big, like, weird capital E. And so there's some different parts of it. So typically we use I or N. I usually use I, but you're going to see that Desmos uses an N here. So I'm just going to write out what it is first. So this is the Greek letter sigma. And sigma in math class just means sum. So whenever you see a capital sigma like that, that just means you're taking the sum of something. So this little lowercase I down here, we call that our indexing variable. And I'll explain more what that means in a second. The 1 tells you where to start counting. And then the N on top is just a number, and that tells us where to stop. And then next to sigma is some sort of formula. So I'm going to kind of write out more explicitly what it is for a Riemann sum, but it can be any formula. And we're going to actually see sigma notation and summations later on in this year when we do series. So for us, you can also use these on your graphing calculator. So while I'm just here and thinking about it, so on the TI-84 graphing calculator, you can get this by going to Math, and then option 0. And I think there's actually, if you have the newer software, there's actually a shortcut to it. Let me see if I can remember it. Or you can hit alpha, and then window. and it's going to be option number 2. It's going to say summation next to it. So if you have a graphing calculator and you don't have it out yet, I would go ahead and grab that and hit one of those key pathways so that way you can see it on your calculator and kind of follow along. So what we're going to do for summation notation is we're going to put a formula in here. And I'm just going to abbreviate that formula as A sub I. So this is a formula, and that's what we're going to plug in. So in this case, since we're using a Riemann sum, it's going to be an area formula. And so it's A sub I. So the I is like our variable here. It acts in place of an x coordinate. So you know how normally like with a function, you plug in an x value, you get out a y value. So here you're plugging in an I value, an indexing variable to say like this is the, so like I equaling 1 means that's the first interval. I equaling 2 means that's the second subinterval, right? I equal 3 is the 3. So right, in our previous examples here, right, I'm gonna go up, where am I? Let's do this one. Right, so this orange rectangle here for our midpoint example, that's when I is 1, because it's the first subinterval. This one would have been I is equal to 2 because it's the second, so on and so forth. So for a Riemann sum, we are using an area formula. Right, so the Riemann sum A sub I is the area formula of a rectangle. Right, so we need the width. So the width is delta x. And then the height is your function value evaluated at the end point. So the endpoint part, you kind of have to figure out. And part of it is kind of looking for patterns. And the right, left, and midpoints, they definitely follow a set pattern, but I don't want to write out what those formulas are. I want you to try and kind of figure them out so you can kind of understand why they are what they are before you just start trying to memorize something. But your delta x is always going to be b minus a all over n, where the b and a come from your interval. So, right, your interval would be on b to a. I'm sorry, a to b. Right, so the a and the b are your starting and stopping endpoints on your x-axis, and n is the number of subintervals. So normally you're going to do equal with, because otherwise your delta x becomes a formula and that just becomes really hard to put into your calculator. So what we're going to do for our last kind of portion of this is we're going to go back and write a formula for each. Right, so go back to the previous example and write each approximation using sigma notation. And verify the answer with a calculator. So now you can use the graphing calculator and Desmos. I'll show you how to do that with sigmas. You can also use those keystrokes I wrote up above for your TI-84 or whatever kind of calculator you're using. If you're using the TI-84, whenever you're putting in your I, instead of using the lowercase I, just hit your variable key and use an X instead. It doesn't matter what the variable is as long as you're consistent. Okay, so let's look at our right endpoints first. Okay, so I'm going to actually cheat a little bit, and we're going to go back all the way here. Okay. Okay, so just wanted to copy this down so that way we could look at it. So we know that these are all of our delta x's. Okay. So what we're going to say here is for our area approximation. Our area is approximately equal to our sigma. So we're going to start at I equaling 1. And we have 4 subintervals. So that's going to tell us what number to put on top. So that tells us to count to 4. And then we're always going to do our delta x. So in this case, it's going to be 1/2 times our function. So now we want to figure out what we want to plug in. So this is I equaling 1, I equaling 2, I equaling 3, and I equaling 4. So some of you might be able to see the pattern, but otherwise you might want to kind of draw a little t-chart here. So we have an I, and then I'm going to call this x sub I, because it's giving us an x coordinate to plug in. Okay, so I have 1, 2, 3, and 4. So this might feel a little reminiscent of algebra 1 actually. So if I plug in 1, I want to get out 1/2. If I plug in 2, I want to get out 1. If I plug in 3, I want to get out 3/2. And if I plug in 4, I want to get out 2. This one's pretty easy. So when you're finding out your formula for your endpoint, because we are doing equal subinterval widths, right, they're all 1/2 width, you're all counting up by 1/2, it's going to feel really similar to writing the equation of a y equals mx plus b line. So you can think about it that way. So if I want to go from here to here, I'm just doing 1/2 times my I value, and I'm getting out my xi value. So I'm going to plug in 1/2 times I. So you could leave it like this because you know what the function is. You could also rewrite the equation of the function. So you could also write it as this, right? So everything is going to stay the same, except here I'm going to multiply it by 2 and then my x value all squared. And that's going to be where the 1/2 I is going to go on the inside. So now you can evaluate this with a calculator. So you can use those keystrokes I told you about on the graphing calculator, or we can go to Desmos. So what I'm going to do, I'm going to show you on Desmos first. There we go. Okay, so I'm going to clear that out. So I'm going to set this up by saying f of x is equal to 2x squared. Okay, and if you want, you can even, if you can use the little squirrely brackets, and you can kind of just tell it where to start and stop. So that way I'm gonna do a little domain restriction there. There we go, see the function really well. Okay, so if you want to get your sigma notation, you're going to go into functions, and you're going to go over to miscellaneous, and then you're going to see that giant sigma down there at the bottom. So you can use whatever letter you want. Like if I scroll over here, I could replace that with an I, but it gives me an N there automatically, so I'm just going to start there. So I'm going to start at 1, oops, not 11, 1. I'm going to count up to 4, and then I'm going to do my 1/2 times, now this is why I said I made it f of x equals in the top line, because now I can just use f, and then I want to do 1/2, and then my indexing variable here is an n and not an I. So whatever that letter is underneath of your sigma is the letter you want to continue using. So I'm going to go pull my n, and then look, once I finish my formula, it's telling me the answer is 7.5, right, which is what we already found from our previous part, right? So we're really just checking all of our answers here. So as we go through this, it's going to get a little faster, and as you get more practice, it becomes even faster. So now let's do the left endpoints. I missed the word end. Good job. Okay. Okay, so again, I'm going to scroll back up, and I'm going to cheat a little bit. Bada bing, bada boom. Okay, there we go. Right, so this is what we had before. So let's set up a little table here. We'll do it in red. Right, so we have I and xi. Right, so the I is our input. The xi needs to be our output. So I'm going to do 1, 2, 3, 4. And then when I plug those I values in, I want to get the x values out. So I want to get these numbers out. So these are my outputs. So again, you have that constant increasing of 1/2, so that would be your slope. So you can actually think of this as solving a y equals mx plus b. I like to think of it kind of as if I worked backwards to plug in what my 0 would be. Like if I put a 0 column up here, I would just go backwards, right? So this is adding 1/2 each time, right? So I have a constant increasing slope of 1/2, which means that if I go backwards, right, I would subtract, and I would have a y coordinate of -1/2, which means that my x sub I is really just equal to 1/2 x minus 1/2, which is also equal to 1/2 times x minus 1. And by x, I mean I, because that is a typo. Right, because we're plugging in an I and getting out the x. So that's what I'm going to plug in for my endpoint. So when I go to set up my area approximation here, we're going to get that it's approximately equal to sigma starting from 1 going to 4 of my width 1/2 times my function value evaluated at the left endpoint, which is 1/2, which is the delta x, times I minus 1. Which makes sense, right? Because if we were using the right endpoint and it was just 1/2 times I, we want to use the left endpoint, we want to back it up 1. So it makes sense to subtract 1. So what I'm going to do is I'm going to go back into Desmos and I'm just going to adjust that formula. So put a parenthesis in there, minus 1. And look at that, it pops out the 3.5. And if you didn't know this about Desmos, if you click on that fraction-y looking button next to it, it'll toggle your answers between fractions and decimals. So it's super handy, just as an FYI. Right, so again, verified our answer, 3.5. So now if we go and do the midpoint I think is the hardest one to set up just because the formula is a little weird. Copy. So now we want to do our sigma with the midpoints, right? What we had originally was this. So our width is still 1/2, right? We're still going to count to 4, so I'm still going sigma starting from 1 and going to 4 of my width of each rectangle times 1/2 times my function, and this is where we have to actually do some work. So yeah, let's do a fun color. Let's do this color. So I need my eyes, and I want them to give me my xi's, right? So if I start with 1, 2, 3, and 4, right? Because those are the 4 indexing values that we're going to plug in. That's why it starts at the bottom of I equaling 1, goes to the top of 4. So I want to get out the values 1/4, 3/4, 5/4, and 7/4. Okay, right, so it's still a 1/2 difference, right? So you're still adding 1/2 each time. Okay, so if I'm writing this as a kind of a line, right? So my x sub I, come on, is equal to 1/2 times my indexing value plus the y-intercept of this line. So think about going backwards. If I were to go backwards by adding 1/2, right, 1/4 minus 1/2 gives me negative 1/4. So my y-intercept is minus 1/4 here. Okay, so you can plug that in just as is. I'm going to do a little bit of tricky algebra here just to rewrite it to maybe look a little bit more formulaic. Maybe that'll help you figure out what's happening here. I'm going to actually make this one fraction first. So if I do that, this is really 2/4 I minus 1/4, which is 2I minus 1 all over 4. Now this is where it's like, why would she do this? I'm going to factor a 1/2 out, right? Because that 1/2 is our delta x, and that has shown up in the other two endpoint formulas, so hopefully it should show up here. So if I factor out 1/2, that's going to give me 2I minus 1 all over 2 on the inside here. And that's what I'm going to plug in here. Right, though you could plug in any iteration of that formula. So any of these you could plug in, this one, this one, this one, or this one that I plugged in to your calculator, and it would all give you the same answer. So I'm going to go back over to Desmos here. Right, so I have that 1/2 in there. I'm just going to delete this out, make me a fraction. So now I'm going to have 2n, and then minus 1, and then in the bottom, all over 2. And hey, look, 5.25, which was exactly the answer that we had before, which means that we got our formula right. So if you know how to find the area without setting up sigma notation, and then you're asked to find it with sigma notation, right, use your calculator to check it. There are formulas to evaluate these without using a calculator. So that way, if you had to find, like, if you went from like 1 to 100 and didn't have a graphing calculator, you wouldn't have to actually add them up. I will put a link up or something on School of G if you're interested in those, but for time's sake, I'm not going to go over those today. So to finish this video off, the last part of your notes here today is for your OYO question, right, go back to the other OYO and write each area approximation from the other OYO question as sigma notation and check your answers using the calculator or using the graphing calculator on Desmos.